Hello friends, welcome you all to online session. Myself Prerana Shinde from the Department of Chemistry, S.V.K.T College, Devai Camp, Nasik. In a last lecture, we have seen the classification of elements on the basis of periodic table. In that, we have seen the different periodic properties, some of the properties like atomic radius, ionization, enthalpy, electronegativity. These properties we have seen in a last lecture. Today, we are going to see the metallic properties, melting point trends, division of periodic table on the basis of, in a last lecture we have seen division of periodic table on the basis of SPDF block, and but the that is transition element, inner transition element, the alkaline metals that we are going to see in this third topic. Next is the physical property. So these are our learning objective for the today's lecture. This is the periodic table. In that we have seen how the atomic radius gets varies, that is from left to right the atomic radius get increases and the electronegativity get increases. These are the some trends that we have seen in a last lecture. Today we are going to see the division of periodic table. How get the periodic table get divided on the basis of, what are their general names on the basis of. So, the elements of modern periodic table, there are 4 different types of elements present in MPT. These elements like elements of main group. In the modern periodic table, group 1 and 2 elements on the left hand side of the element of the group 13 to 17 on the right hand side known as a main group element. These are called as a representative element. The group first and second, that is the alkali and alkaline earth metal, these are the representative element. This is the hydrogen family and the beryllium family. Here the indication that is a group first A, group second A. These are also known as the representative elements. The division of periodic table on the basis of representative element, noble gas element, transition and inner transition element. So, where is the representative element or the alkaline earth metal situated? That is a group first and second element on the left hand side of the element, and group 13 to 17 on the right hand side of the are called as a representative element. Generally the S and P blocks are called as a representative element, where the S block contain the two families, that is hydrogen and beryllium family, and the P block contain boron, carbon, nitrogen, oxygen, the halogen and the noble gas family. So from group 13 to 17 is what the representative element. Noble gases, the elements of group 18 are called as a noble gases. They are not reactive, they are also known as a inert gases, as they have the outermost shell is completely filled. That is the helium, neon, argon, krypton, xenon, radon. These are the noble gases. That they are also known as the inert gases, or they are not much reactive, therefore they are noble gases. The next is the transition element. The elements belonging to group from 3 to 12, that is the middle of the periodic table, called also known as the D block element, known as the transition element. That is, the two outermost shells of this element are not completely filled. Inner transition element, ती स्लाइड ना कट झाली अर्धी ॲक्च्युली, कट झालेली स्लाइड खूप इकडे झाली, इथे अशी दिसते. नाही, पूर्ण अर्धे अर्धे वर्ड्स इथले कट. टी नाही दिसत, टी दिसतच नाही. इनरचं पण ॲड दिसत नाही. इनर हो दिसेल का तिकडे? मला काही प्रॉब्लेम नाही, पण तिकडे दिसेल का? हां, इथं कटिंग ठीक आहे. ही स्लाइड परत करते. तुम्ही म्हणजे फक्त स्टार्टिंगच केली होती, पण मला वाटलं कटिंग झाली. The transition element which belongs from the group 3 to 12, that is the middle of periodic table, are known as the D block, also known as the D block element. In the periodic table, which has the two outermost shells of element are not completely filled. They show the transition, that is the DD transition. They situated in the middle of the periodic table. Inner transition element, these are the two rows. The inner transition element has a two rows, that is say the F block comprises of two rows, that the lanthanide series and the actinide series. From 58 to 71, these are the lanthanides and the actinides. The second row that is from 90 to 103 metals placed on the left hand side of the modern periodic table, the actinide series is placed. These are generally the radioactive elements from lanthanum and the actinide series. Group 1 elements are called as alkali metals and group 2 elements are called as alkali earth metals. To the right hand side of the modern periodic table, there are non-metals, that is a boron, carbon, nitrogen, these oxygen, these are the non-metals. Metallites placed diagonally from boron to polonium, these are known as the metallites. They shows the both properties of one metals and non-metals known as the metallites. In a boron family, aluminium, gallium, indium, thallium, these are the metallites. Next trend is the melting point. How the melting point get vary from right to left or from metal to non-metal character. But basically what is the melting point? The melting point is the amount of energy required to break a bond to change the solid phase of a substance to a liquid. Generally, stronger the bond between the atoms of an element, the more energy required to break that bond, because of temperature is directly proportional to the energy. This is the definition for the melting point of the particular substance. But how get it vary according to the periodic table? Metal generally possesses a high melting point, non-metal generally have a low melting point. The non-metal carbon possesses the highest melting point of all the elements. The semi-metal boron also possesses the high melting point. These are the two exceptions for this, that is non-metal and the semi-metal. These are the hot point you can say. The metallic character trend. The metallic character of an element can be defined as how readily an atom can lose an electron from right to left across a period. Metallic character increases because the attraction between the valence shell electron, that is the electron which is the which is in the outermost shell, and the nucleus is weaker, enabling the easier loss of electron. Metallic character increases as you move down the group because the atomic size is increasing. When an atomic size increases, the outer shell is further away. As you can take example of a sodium, potassium, calcium, these are the metals in the periodic table. The metallic character trend, that is the principal quantum number, increases and average electron density moves further away from the nucleus. The electrons of the valence shell have less attraction to the nucleus and as a result can lose electron more easily. This causes increase in metallic character. Here you can take example of sodium, as it has electronic configuration of 11. So, for completion of last shell, that is you can divide it according to 2, 8, 1. So, for a sodium metal, it will easy to lose 1 electron instead of gaining the 7 electrons more. So, as it can lose 1 electron more easily, so it acts as or it shows the properties of a metal. Move left across a period and down the group, increasing the metallic character. Move right to the across the periodic table and up to the group, decrease the metallic character. So you can say from the left of the periodic table there are metals are there, and to the right there are non-metal. Next is the valency, one of the most important factor in the modern periodic table. How many number of bonds can form by particular element in their particular state. So one of the trend in modern periodic table is that the valency of an atom. As you already know, the valency of an atom is the number of electron it has in an outermost shell or the number of atoms in a required to complete its outermost shell. Or one can determine the valency of element simply from its position of the periodic table. The group that the element is placed is usually indicates its valency. Let us look at few examples to understand the trend. Here you can take, that is a carbon. Carbon has a valency 4. As you know the atomic number, from that you can conclude to the electronic configuration and how many number of electrons it required to complete its octet, that much bond it can form. Carbon, you can write it as a 1s2, 2s2 and 2p2 electronic configuration as it has a atomic number 6. So 1s2, 2s2, 2p2. So p orbital has a 6 number of electron capacity. So it can accommodate 4 more electron, therefore carbon can form 4 more bond with respect to that. Even you can take example of a sodium. It has a atomic number 11, so you can differentiate as a 1s2, 2s2, 2p6, 3s1. It can accommodate 1 electron or can lose 1 electron. So it has a valency of a 1 number of electron. It forms a bond. Here you can take example of sodium chloride. It accepts the 1 electron from sodium. It loses electron to the chlorine in the ionic bond with the NaCl, and chlorine has a capacity or can accommodate 1 more electron, as the halogen have a capacity of 1 electron. The general electronic configuration for the chlorine, that is NH2NP5, so it can accommodate 1 more electron. Chlorine has tendency to accept electron as it has a more electronegative value. So it just accepts electron from sodium and get fulfilled, and sodium loses its electron and get fulfilled and complete its outermost orbital. So this is all about the valency. So how much number of bond will get formed by particular element is all about the valency. Next is the bonding. There are different kinds of bonding, that is a covalent bond, ionic bond, covalent coordinate bond. So which kind of bonding particular element get formed with get attached with the particular element. So as you move across in a periodic table, the types of commonly encountered bonding interaction changes, because at the beginning of periodic table, elements such as a lithium, beryllium, which has a capacity, the lithium, that is a 3, 1s2, 2s1, beryllium 4, form a ionic bonds. They can easily use electron. So in a general, they form the ionic bonding. Moving across the period, there are boron, carbon, nitrogen, oxygen tend to form the covalent bond. They just get shared electron, because it is very difficult for them to donate all the electron, as they have some of the electron with them. So they just get shared their electron with the neighboring atom. Fluorine can form an ionic bond with some elements such as a carbon and boron. Neon does not tend to form any bonds at all, because neon, helium neon, as you can already we have seen in a last slide, that is helium, neon, argon, krypton, xenon, these are inert gases. They have a fulfilled their octet, so they are not easily shared their bonds at all. The next is the physical properties, that is the melting points of the halide. That is another physical property that varies across the period, that is the melting point. A halide is a binary compound. Fluorine, chlorine, bromine, they form a, that is a F2Br2Cl2. They form a binary compound, of which one part is a halogen atom and the other part is a element or a radical, that is the less electronegative than the halogen, to make it fluoride, bromide, iodide, acetate compound. All group first metal form halides that are a white solid at room temperature. Sodium chloride, potassium chloride, sodium fluoride, potassium fluoride, they form the halide and they are generally solid at room temperature. As you can take your daily life example, that is a sodium chloride, which is a white solid and which really has a high melting point. All the alkali halides and alkaline earth halides are solid at room temperature and have a high melting points in hundreds of degrees centigrade. For example, the melting point of sodium chloride, that is 808 degrees Celsius. In a contrast, the melting point of a non-metal such as a carbon tetrachloride, phosphorus trichloride are below 0 degrees Celsius. So these materials are liquid at a room temperature. Furthermore, all these compounds have a low boiling point, typically in the range of 50 to 80 degrees Celsius. These are the organic solvent, that is carbon tetrachloride, phosphorus trichloride. These are the organic solvent. They get easily vaporized because as they have a really low boiling points. Next is how we have seen the so much periodic properties, that is atomic radius, ionization enthalpy, valency, melting point, their bonding nature. We have seen the Mendeleev's law, how the atomic weights, atomic number, we have seen all this kind of thing. But what is the basics of all these things is the electronic configuration. How the electron, what are the electronic configuration first of all, and how to write the electronic configuration, what is the need to write the electronic configuration. electronic configuration is nothing but the address of that element in a periodic table. So, if you want to particularize a element where it located in the periodic table, we can say it along with the electronic configuration. Electronic configuration, it has a in which block it is, how many number of electron it has. So, this is all about the electronic configuration. So, here in this slide we are going to see what is the electronic configuration, how it write, and what are the rules to write the electronic configuration, what are the correct criteria to write the electronic configuration. Basically, what is the electronic configuration? In daily life, we can say it as it is the address of a particular element. The electronic configuration of an element describes how electrons are distributed in its atomic orbital. As you already seen the S, P, D, F orbitals, in according to that it will get situated, that is S orbital, alkali, alkaline, earth. P, non-metals are there from 3 to 12. D, that is a middle of the periodic table. F is the all the radioactive elements are there. So, S, P, D, F are the atomic orbitals. The electronic configuration of atom follow a standard notation in which all the electron containing atomic subshells with the number of electron they hold written in the subscript are placed in a sequence. For example, the electronic configuration of sodium. So, first of all you should know the atomic number of the sodium. So, what is the atomic number of sodium? That is 11. Sodium has 11. You can write according to K elimination, that is 281 according to the K elimination. But for a particularize, you have to write in which orbital the electron gets situated, how many number of electron get. So, there are some rules to write the electronic configuration. First of all, we can see how to write the electronic configuration. What is a 1 over here, what is a S here, what is a spin quantum number. In our previous lecture, we have seen the different types of quantum number: principal quantum number, azimuthal quantum number, spin quantum number. So, here is a 1 is a principal quantum number, energy level, in which energy level the particular electron belongs. S, that is a which type of orbital, and 1, that is a how many number of electron in that particular orbital is there. These are the some images that I have taken from the internet or Google Chrome. So, there is a one more criteria to fill up the energy level. So, this is a trend: 1s, 2s, 3s, 2p, 4s, 3p. So, from the 1s you can goes to 2s to the 2p. After the filling of 1s energy level, you can fill 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. There are some arrows are given according to the energy level, that is if n equal to 1, 1s, n equal to 2, 2s, n equal to 1, what it indicates? It indicates the principal quantum number. So, after the filling of 1s energy level, there is a fulfillment of a 2s, 2p, 3s, 3p, 4s. Here 1, 2, 3, 4, 5 indicate the principal quantum number or the energy level. S, P, D, F, that is the atomic orbital. In that we have seen the S orbital has a maximum 2 electron capacity, P orbital has a maximum 6 electron capacity, D orbital has a maximum 10 number of electron capacity, and F orbital has a 14 number of electron capacity. So, what are the rules to write the electronic configuration? Here first of all is the Pauli's exclusion principle. The Pauli's, what it said? The Pauli's exclusion principle states that a maximum of 2 electrons each having opposite spin can fit into an orbital. If I take an example of an S orbital, S has a capacity of a 2 electron. So, how the electron get filled? First of all, any orbital has the capacity of maximum 2 electron. Not more than 2 electron you can fill, not a 3, not a 4 electron you can fill. You can fill up to the only 2 electron. But how? The spin should be opposite, that is a plus half and minus half, which is in upward direction and another is in a downward. The principle can also be stated as a no 2 electron in the same atom have the same values of all 4 quantum number. All 4 quantum number, that is the principal, azimuthal, magnetic and spin. These are the 4 quantum number. We already seen in a last or a previous lecture. So, Pauli's exclusion principle state that No two electrons in the same atom have the same set of 4 quantum number. Therefore, if the principal, azimuthal, magnetic quantum numbers are the same for 2 electrons, they must have the opposite spin. If any either 3 quantum numbers are same, the force should be different. Here you can say if has a same number of principal quantum number, same number of azimuthal quantum number or magnetic quantum number, they should have the opposite spin. The next is the Hund's rule. What Hund's rule says? This rule describes the order in which electrons are filled in all the orbitals belonging to the subshell. It states that every orbital in a given subshell is singly occupied by electron before the second electron filled in an orbital. Here I can take the example of a p orbital. P, there are 3 subshells in that p orbital. So firstly, all the first electron get filled first subshell. After that, only the pairing is possible. It also states that every orbital in a given subshell is singly occupied by electron before a second electron is filled in an orbital. In order to maximize the total spin, the electrons in the orbital that only contain one electron all have a same spin or the same values of spin quantum number. Here practically you can see, here is the 1s2, 2s2, 2p2 configuration of the carbon. It has a number of 6 electron. So how you can fill? Both the ways are shown here, that is the correct way and the incorrect way. The first, the atomic number, that is a 1s2, 2s2, 2p2. The general term, that is the number of electron capacity of s orbital, is the 2 electron. P has a 6 number of electron. So first of all you have to fill the 1s2 according to the energy level diagram. After that you can fill 2s2 and after that you can fill 2p2. But how? According to the Pauli's exclusion principle, these 3 orbital has a different, these 2 electron do not have a same set of quantum number. Here you can feel, here is a correct image, that is 1s2, one with the one electron with the opposite spin, that is 1s2 filled with the opposite spin. Incorrect way, that is see here 1s2, 2s2, 2p2. Pairing is already happened, but that is not possible. According to Hund's rule, what it said, the electron are filled in all orbital belonging to the subshell. First upon electron get filled 2p1, that is a 2px, 2py and 2pz. Then only get the pairing is happen. So then only the 2p2 is possible in here. So these are both way are shown here, that is a correct way and incorrect way. These are 2 most useful principle to filling of the electronic configuration. So this is all about the how to write the electronic configuration, what are the subshell, how, what Hund's rule says, what is the Pauli's exclusion principle. In a summary you can write it as a Pauli's, no 2 electron have a same set of 4 quantum number. Hund's rule says that the pairing will not possible, instead of that the filling of a single electron in a particular subshell is there. So this is all about the principle and how to write the electronic configuration. Electronic configuration is the address of element in a modern periodic table. So these are some electronic configuration of the noble gases: helium 1s2, neon, helium, that is it has a completely filled octet, 2s2 and 2p6. So these are the some electronic configuration or the exercise you can say. So this is all about today. In that we have seen the periodic properties, in that we have seen the valency, bonding character. After that we have seen the melting points of the halides, what are their nature, how they get varied according to their bonding. If they form the ionic bond, they have a high melting point, and how to write the electronic configuration. So this is all about today. Here is the exercise for you, that is assignment on the basis of periodic trend, that is the ionization energy. Which element has the highest ionization energy among the following? Fluorine, nitrogen, helium. The element which required, here you can use the definition for the ionization energy, which has a completely or half filled electronic configuration has the high ionization energy. So, here you can conclude the nitrogen. Nitrogen has a larger atomic radius than oxygen. From the periodic train from left to right, how it get varied, you can take the hint, you can use it as a hint. Which has a metallic character, lead or tin, today only we have seen. Which element has a higher melting point, chlorine or bromine, that is from top to bottom how the melting point get vary. Which element is more electronegative, sulfur or cesium. In a previous lecture we have seen the electronegative train. So, this is all about today. Thank you.